In these notes, we're taking a look at a third type of vector multiplication. In the previous lesson, we were introduced to two other types. First, the multiplication of a vector by a scalar, which leaves us with another vector. So basically, whatever that scalar is, it increases or decreases the magnitude if that value is less than 1. If it's negative, it reverses the orientation of the vector. So vector times a scalar gives us another vector. And then the main focus of the last lesson was the dot product. So the dot product gave us a scalar. So we take two vectors, multiply them using the dot product formulas, and you end up with just a number. And so in our lesson today, we're taking a look at a third type of vector multiplication where we multiply two vectors in such a way that we end up with a new third vector that is perpendicular to both of the original two. So that's what we see in the diagram in front of us. So we have these two vectors A and B, and so they are in some flat surface. It doesn't necessarily need to be the xy coordinate plane. It could be located anywhere. But this cross product that we're going to end up with, this new vector, is perpendicular to both of those original vectors. So it's perpendicular to the plane that contains both the vectors A and B. So one method of arriving at this cross product vector, and again remember it is a vector, is to take the magnitudes of the two vectors, A and B, multiply those times the sine of the angle. Remember in the dot product formula it's the cosine of the angle between the two vectors. And then for the dot product that would be it. But we also need to have the components of a vector that's normal, another term for perpendicular, to the plane that contains both A and B. So the first three parts there, the magnitude of A, the magnitude of B, the sine of theta, those are all obtainable and easy to calculate. So together, these make up the magnitude of the cross product. And so then we need to multiply that magnitude times the components of the unit vector that is normal at right angles to both A and B. Now that last part is a non-trivial piece to obtain. And so typically we're not going to use this formula to help us find the components of the cross product vector. We can use it to find the magnitude, because again, magnitude of A and B, easy enough because of the 3D Pythagorean theorem. Finding the sine of the angle is doable since we have the dot product to help us find the angle between the two vectors. But the components of that unit vector normal to the plane is not something we're going to be able to come up with very easily. So to find the components of the cross product vector, we're going to have to go about it a little bit differently. So what is the orientation of that cross product vector? If we go back to the diagram that we have here, I have that cross product going upwards. But it could have just as easily have gone down and still been perpendicular to the plane containing the vectors A and B. So how do we know which direction that cross product vector is going to be oriented? Is it going to be up or is it going to be down? So we have a 180-degree difference between those two. Well, the tool that we have for that is called the right-hand rule. And so hopefully this is familiar from your days in Ms. Guthrie's class. But the rule there is you take your fingers and you point them in the direction of the first vector. So again, if we go back here to this picture, and I'll go ahead and clear everything so we can see a little bit more clearly, I would point my fingers, so I'd have to really bend my hand back towards myself, in the direction of A. And then I would curl those fingers towards the second vector, so towards the vector B. And so then the direction that my thumb is pointing, that is going to be the orientation of the cross product vector. And so in this case, we can hopefully picture that that would be up. So that would mean that if we did B cross A, if we reverse things, so if I started with my fingers oriented in the direction of B and then tried to bend them around this way, I'd have a real tough time bending my fingers, so I'd have to flip my hand around in order to be able to curl them towards the vector A, which then would force my thumb to orient downwards, and so then I would have the cross product vector oriented 180 degrees opposite. So what again this tells us is that the cross product is not commutative. You do not get the exact same result when you reverse the order of the vectors that are involved. So in the interest of time on this next example, I've pre-drawn the diagram that we have here, so you may want to pause for a moment and copy that down. But we have the vector A is in purple here, so we have 6 root 3 as our I component, 6 as our J component, so we've got that sketched out. And then the blue one is the vector B, so we're negative 8 in the x direction. I just labeled it with a positive 8 just to ignore the negatives, and positive 8 in the vertical direction. So we've got a sketch here, so we're trying to find the cross product, the magnitude of the cross product of these two vectors. So the formula for that cross product is going to be the magnitude of A times the magnitude of B times the sine of the angle that's in between them. So there's 3 pieces of information that I need. So the first is the 2 magnitudes. So again, hopefully we're recognizing these as being special right triangles. So in the case of A, we have a 30, 60, 90 triangle. So that means the hypotenuse, the hypotenuse is going to be double the short leg. So we're going to get 12 as that magnitude. Then for B, we hopefully see that as a 45, 45, 90 triangle. So to get the hypotenuse, we're going to multiply by root 2. So we've got 8 root 2 is the magnitude of B. And then to find the angle, we could, if it was necessary, if the angles weren't so simple for us to work with, we could use the dot product. If you'll recall, the dot product is the main vehicle for finding the angle between two vectors, certainly for vectors that are in 3 dimensions. But in this case, since I know this is 30, I know that's 60 there, this must be 45, so together I can add these two together, and that's the angle between my 2 vectors, so that's going to be 105 degrees. And so now I've got everything that I need to be able to find the magnitude, so I just need to multiply 12 times 8 root 2 times the sine of 105 degrees, and just so that we can continue our process of rounding off to arbitrary places in our notes, we can say it's 131.1 is going to be the magnitude of our cross product. So we can write it like this. Now, additionally on this one, we could actually go so far as to write the cross product vector in component form. And the reason we can do that here is because of that right-hand rule. Since we know that the cross product is going to be perpendicular to the plane containing the vectors A and B, well, in this case, the plane containing the vectors A and B is the xy coordinate plane. So that means that to be perpendicular to that plane, we're going to be just oriented in the z direction. So if you can imagine, you can just put your pencil at the origin here, pointing straight up, and that's going to be the orientation of our vector. And it is going to be up, not down deeper into the screen. The reason being the right-hand rule. If I curl my fingers from A in the direction of B, my thumb is going to be pointing straight up at me, and so that means that the component form of my cross product vector is going to be this 131.1 just k, because it has got no x and no y components if it's going to be perpendicular normal to the plane containing A and B.